Hi, in this video, we are going to design the first schematic using Sky 130 nanometer open PDK. We are going to go back to we are right now in projects folder. So inside projects folder, I'm going to make a test folder. Go inside test. And then we're going to invoke the Xschem. So how to invoke the Xschem? We have this information on this website called Xschem Sky130 integration. So here, after installing the PDK, there's information. Inside the directory, we copy this Xschem RC file. And then invoke the Xschem. So it opened the example circuits, and then we can create a new schematic here. There's another one way to actually this one using this terminal, so we are not able to use terminal. There's another way to use it. Actually, it's this information available in this website. It highly suggests that we use Xterm. We use Xterm, so it open up another terminal and free up this terminal for other operations. And then set the terminal. Okay. Now, did we copy that? Yeah, we already have this Xschem, right? So instead of invoking the Xschem here, first open the Xterm. It will open up this one and free up this one. But one little details here. So as you can see, the terminal here, we are not able to use it, right? Unless we close this Xterm. So the best way is to, sorry, I need to go back to this EDA tools. Oh, sorry, not EDA tools. It was in the projects test. One small detail, so Xterm and this AND symbol. And as you can see that while we are invoking, we are using this Xterm to use the Xschem. But here, this original terminal is free to use for other operations. So here, test, inside test, we already copied this Xschem, and then directly here, invoke the Xschem. Open up a new schematic here. So we are going to design the inverter using the Sky 130 nanometer. Click Shift I. So inverter, basically we have PMOS and the NMOS and voltage sources. Voltage source for the power supply VDD, and for the input, basically we just give input as a pulse of square wave as input to the inverter, and we look at the output. So all the basic files will be available as primitive files here in the devices. inside Xschem itself, not related to PDK. When we use the process dependent devices like NMOS, PMOS, FETs, BJTs, capacitors, resistors, then we are going to use this Sky process. So inside here we have a search here. Just search vSource. So vSource symbol. This is the you can double click or just click OK. Put one. Control C, Control V. Before going that, make sure that we save this one. Save as. Basically, so we are inside this test folder that we created. So name the file as, okay, name it as test inverter. Okay, and then we are going to place the PFET and the NFET. So that will be inside here, Sky130 FDPR. And if we search here NMOS or NFET, we're going to use this one, NFET 01V8. So this is this process working in 1.8 volt. So that's why 1V8. Double click, place the NFET here, and then search PFET. Here, and then make a connection. So this one is I have to admit that this make connection is not very good in this Xschem. For example, if here I want to make a wire here, so the cursor pointed at this gate terminal and then click W, take it. So if I click and I want to make a turn, but it cannot. So I have to here again press W, click. If I right click, nothing happens. So here again W. So even LT Spice is better than this on the wire connections, but I don't know, this one is really disaster. For example, if I move here, it does not move on the two sides. This is really disaster. This is this has to be improved. Here sometimes if I click W, it does not respond. Now we are going to place the pins. So here is VDD. So basically that is here Shift I. If we go back up in the Xschem device, this is called pin. Okay, it's a lab pin, I remember. Yes, a pin. Now we can just copy paste this one, Control C, Control V, Control V. So this one we need to flip it. I remember it's I think it's a flip in place select. Okay, good. And we are going to place the ground here. Control C, Control V, Control V, and then we are going to place the ground symbol. Shift I, search GND symbol. Control C, Control V, Control V, Okay, now we're going to name the pin net labels. So this one we are going to name it as V out. Here V in. So after you enter the name, if you click enter, nothing happens. So you can try shift enter. Shift enter. It will make changes, and click OK. So here that one will be VDD. Shift enter. And then here let's make this one as actually we can connect directly, but when the schematic is much more complicated, it's better to use the label nets. V in, and this one we are going to use it as VDD. Shift enter. Now we're going to give the values. It basically VDD should be a 1.8 volt. Let's change the name of the voltage source also, VDD. And this one V in, and the value. So this one should be pulse wave. And if you ever used LT-Spice, it's basically same as the LT-Spice. But let me, we can check the on Ngspice to check how we can insert this value. If you search Ngspice manual, let's check it. Ngspice manual. Let's search pulse. Okay, pulse. Okay, we have it here. So low value, high value, time delay, time rising, time falling, period. I believe this is the width, period, and so basically here we have it here. It's pulse width and the period. Okay, with this one. Paste it here, and we have to use this quotation mark. Paste it, and low value is 0, high is 1.8. Let's use time delay of 1 nanosecond, time rise 1 nanosecond, time falling 1 nanosecond, and then pulse width we can use let's say 5 nanosecond, and the period we can use 10 nanosecond. And this number of period we don't need to enter. It's same as LT-Spice. Okay. Now, in order to simulate, we need to add one more thing. Shift I, inside here, search code shown. Here. So basically from here we need to include the process. You need to include the process and what kind of simulation you do. Basically we are doing here transient simulation, and the library, it's available on their website. When we look at the Xschem Sky130 integration, how to include the model. So basically it's here. We need to include this line. The PDK is here. Let's have a look. This one is actually what's inside there. If we go back to if we go inside this user, and let's go to ngSpice. Let's go to this directory, and inside here we have skylib. So basically we have this spice. We have this spice file here, and then TT means the typical corner. And here we have all the SS, SF, FS, and the FF corners. So we just need to simulate the typical corner. Basically just copy this one. Value equal to blah blah, delete that one, quotation mark, and then include that library. And then we need to include this transition simulation. Let's make it a step of 1.1 nanosecond in total of 100 nano, and then save all, basically save all the voltage signals, and click OK. Why this one does not change it? Oh, sorry, I forgot this quotation mark. Okay, don't forget that quotation mark at the end. Let me bring this one down here. Okay, schematic is ready. We include the PDK and transient simulation. Save it, and then let's click on this netlist. Oh, if there's a mistake there, then it will show it here. Undriven node net1 and net2. What is net1, net2? Okay, I think we didn't connect this the bulk of the MOSFETs. This making connection is really disaster. There's no way this one close to cadence, but at least this is free software. Okay, save it. Now if we click on netlist, so it turns green. That means there's no errors here. One thing I like is that in the simulation tab, show netlist after netlist command. So if we click on netlist command, it shows us the netlist. If I click net command, now it shows our net list of the schematic. Basically, this schematic is inside this folder called test inverter, sub circuit test inverter. We have a voltage pulse voltage source. The two terminal is V in and the GND, and this pulse. And then this is the spice, right? If you familiar with the spice. Another voltage source is VDD, ground is 1.8 DC voltage, and the MOSFET one. So it's basically the drain, gate, source, and the bulk, and the some parameters. It's NFET. The length is 0.15 micrometer. The width is 1 micrometer, and all the peripheral parameter. Next is MOSFET 2. That is P. The drain. Drain is V out, gate V in, source, and the bulk. And this is the PFET. Same length and width. And we include the library, typical corner, transient simulation, and the save the voltage signals. Okay, save it. Now we are going to simulate. Click simulate. Click the simulate. Okay, there's no error here. Now, in order to show the plot, we can just typically type plot V in. What are the nets V in and the V out? Click. No such director V in. Oh gosh. Okay. Plot V out. Okay. Before that, let's see in the simulation, configure simulator and the tools. ngSpice iDirective. Maybe we need to click on this one. Accept, save, and close. Netlist. Save it. Simulate. No comment. Run simulation aborted. No data saved for transient analysis. Analysis not run. Analysis not found. I think I make a mistake on here. Maybe there should not be this star symbol here. Okay, save all. Click netlist, save, and simulate. I think this time it's gonna be saved. Okay, this time it saved the voltage signals. Now let's see plot V in and the V out. Okay, plot it. Now this is not that user friendly. I'm also very new to this Xschem, and there's a lot things to learn. But basically, if you want to zoom in, just right click of your mouse and drag and zoom in the region to see. It opened a new window here. You're seeing the. So that is the V in. When V in high, V out is low. That is the basic inverter. Thanks for watching.